our current concept of sine of theta, cosine of theta, and tan of theta are based on a theta, which is an acute angle that lives inside a right triangle, based on which there's an opposite side, an adjacent side, and a hypotenuse. Now, what would happen if we considered that same acute theta on the unit circle? Well, the first thing to know is that since theta is acute, the terminal side is going to land somewhere on the first quadrant, like this picture shows. The second thing to notice is that this is a circle and this is a triangle, and so there's no reason to expect that sine and cosine are going to appear in some nice way in this picture. But not only do they appear in the nicest way they can possibly appear. And in order to see that, we need to first think about this point right here, which is the point on the unit circle, which corresponds to a rotation of theta. Let's call that point x comma y. And from that point, I'm going to drop an altitude to the positive x-axis. And now the bridge is beginning to be built because we see a right triangle. What's the hypotenuse of that right triangle? Well, isn't that just a radius of the unit circle? So that would just be 1. Okay. Well, how long is this side that we just created? Well, isn't that just how far above the x-axis that point is, which would just be the y-coordinate of that point? So this side length is just y. And what would be the last side length of this base that's along the x-axis? Well, wouldn't that just be how far to the right that point is from the y-axis, meaning it's just the x-coordinate of that point? So this length right here is simply x. Okay. Based on our current definition of sine of theta, what is sine of theta? So sine of theta is opposite over hypotenuse, so that would be y over 1. That would just be y. Interesting. What about cosine of theta? Well, that's adjacent over hypotenuse, so that's x over 1, which would just be x. And that's interesting because this gives us a new way of thinking about sine and cosine that has nothing to do with right triangles. For any acute angle theta, we could think of sine of theta as the y-coordinate on the unit circle after rotating theta. Nothing to do with right triangles. And we could think of cosine of theta as the x-coordinate on the unit circle after rotating theta. What's nice about this new definition of sine and cosine is that it's totally consistent with our original definition of sine and cosine, meaning when you plug in an acute angle for theta, you're going to get the same answer based on this connection that we've established here. What's nice about this new definition is that it's going to work on theta values that are not just acute. So for an obtuse angle, for example, that has a terminal side in the second quadrant, you're still going to be able to talk about the sine of theta and the cosine of theta. And if you think about it, the cosine of theta is actually going to be negative there, which is an interesting development. The other thing that this new definition does is it tells us things about sine and cosine that are true, that were always true, which we might not have ever known. For example, one thing that's true about any angle theta at all is that cosine of theta squared plus sine of theta squared is always equal to 1, no matter what. And the reason for that is because for any angle theta, that's going to correspond to some point on the unit circle. And by definition of cosine of theta, the x-coordinate of that point is cosine of theta. And the y-coordinate of that same point, by definition of sine of theta, is sine of theta. And so cosine of theta and sine of theta are always going to correspond to the x-coordinate and the y-coordinate of some point on the unit circle. And every point on the unit circle satisfies x squared plus y squared is equal to 1. So by simple substitution, you can determine that cosine theta squared plus sine of theta squared is always equal to 1. So if you ever have just one of them, like sine or cosine, and you need to find the other one, this equation will probably come in very handy. What about tan of theta? How can we define tan of theta in a way that's consistent with the way that we've previously defined it? Well, one thing we can do is, if you think about it, in our old definition, one way to get tan of theta is to divide sine of theta by cosine of theta. Because the numerator of sine is opposite, and the numerator of cosine is adjacent, and they have the same denominator, which would cancel out. So when you divide sine by cosine, you actually get tangent. So one safe way of defining tangent in a way that keeps it consistent with our old definition is just to say tan of theta is just sine of theta divided by cosine of theta. And you might be wondering, is that the only way to think about tan of theta? Wouldn't it be nice if there was a more direct way to think about what tan of theta is instead of thinking about what sine is and cosine is and then dividing them? The answer is yes, there's a nice way of thinking about what tan of theta is, and it has to do with slopes. So if you rotate by theta, you're going to end up with a radius in some terminal position. The slope of that radius, you can show, is the tan of theta. So if you want to know what tan of theta is, you just need to approximate the slope of that radius, which is some positive number. So just based on looking at it, you can tell tan of theta is positive for that particular theta. It begs the question, though, why is that true? Why is it the case that the slope of this radius is always the tan of theta? And to do that, let's just compute the slope of that radius. If that point right there is 0, 0, to find the slope of the radius, all we need to do is change in y over change in x for those 2 points. And so let's go ahead and do that. And we would get that the slope is y minus 0 over x minus 0, which is just y over x, which is sine of theta over cosine of theta, which we know is tan of theta. So that's another way you can interpret tan of theta as not just sine over cosine, but as the slope of the radius once you've finished spinning around theta. All right, now that we have definitions for sine, cosine, and tangent that are new, let's start working with them to solve some fun problems. Our first problem is to figure out these 3 trigonometric values. Now going forward, you should make the assumption that if you're dealing with an angle and there's no unit given, that the unit is radians. So for example, 5 pi over 6 in this problem, you should assume is in radians. Now, when we think about trigonometric values, the mental canvas that we want to be using is the unit circle. And because we're going to be using it so often, I would strongly recommend that you learn some very special angle values and where they are on the unit circle. Specifically, 30, 45, 60, 90, 180, and 270 degrees are very important. And you should also learn those angles in radians. So for example, it shouldn't take you that long to know that 30 degrees and pi over 6 radians are the same exact angle measure. Now, in the past, we have figured out the sine and cosine of 30 degrees, 45 degrees, and 60 degrees, which means technically we know exactly what the coordinates of the points on the unit circle are that correspond to those angle measures. So we could assemble that information over here, and using this information, we can actually figure out each of these 3 trig values. So let's go ahead and do that. So cosine of 5 pi over 6, what's that? Well, first we need to think about what is 5 pi over 6? Where is 5 pi over 6 radians on the unit circle? One way to think about that is to know what pi over 6 is. Pi over 6 radians is 30 degrees. So if you have that internalized, 5 pi over 6 is just 5 of those. So it's 5 times 30 degrees, or 150 degrees. Another way to think about 150 degrees is not quite 180 degrees, but 30 degrees less than that, right? So we could think about it additionally as 180 degrees minus 30 degrees, which should make it clear that the way that it would look on the unit circle is as a reflection of this 30-degree radius over the y-axis. We would get something that looks like this. Another way to think about where that quite exactly is 5 pi over 6 radians. It's almost pi radians, right? So it's almost pi radians, which would be exactly 180 degrees, but it's 5/6 pi. So it's actually pi over 6, or 30 degrees less than that. So pi minus pi over 6 is another way to think about what that angle is. Now, since it's a reflection of this radius over the y-axis, that means the x-coordinate of that point is just the negative of the x-coordinate of that point, which we know is the cosine of 30 degrees, which we know is root 3 over 2. So long story short, the cosine of 5 pi over 6 is negative root 3 over 2. The sine of this angle is the y-coordinate of that point, and when you reflect something over the y-axis, you don't actually change its y-coordinate at all. So it's the same as just the sine of 30 degrees, which is 1/2, which is interesting. So the sine of 5 pi over 6 is simply 1/2. All right, what about the tan of 270 degrees? Well, that would be the sine of 270 over the cosine of 270, which is the y-coordinate of that point, which is -1, over the x-coordinate of that point, which is 0, which is undefined. And that's actually the correct answer. That tan of 270 degrees is indeed undefined. Another way to see that is tan is the slope of the radius associated with that, which is a vertical radius. And as you know, vertical lines also have an undefined slope. Next problem. What about cosine of -pi/3 and sine of -pi/3? Well, where is -pi/3? If pi/3 is 60 degrees and it's about there, -pi/3 is the same amount of rotation, but just in the opposite direction. So the end result would be sort of a reflection of this pi/3 radius over this time the x-axis. And so it would look something like this. And when you reflect something over the x-axis, or you rotate in the opposite direction, as you can see by the symmetry of the circle, the x-coordinate is actually the same as if you rotate it this way. And so the cosine of -pi/3 is actually the same as the cosine of pi/3, which is 1/2. And when you rotate the other direction, or you reflect something over the x-axis, the y-coordinate is negative of what it used to be. So if it used to be √3/2, now it's the negative of that, or negative √3/2. In fact, you can generalize this result. Whenever you have an angle theta and negative theta, those are reflections of each other over the x-axis. And for that reason, their x-coordinates are always going to be the same, like in this case of pi/3 and -pi/3. So you can conclude that cosine of negative theta in general will equal the cosine of theta. And the y-coordinate, how is that going to change? So how is the sine of negative theta going to relate to the sine of theta? Well, since it's reflected over the x-axis, it's going to be the negative of that y-coordinate. So sine of negative theta is the negative of the sine of theta, which is what we just applied to answer this problem. Next problem. This question asks you to determine whether certain quantities are positive or negative, starting with tan of 3. Now, you might be tempted to think that that's 3 degrees because there's no pi in the situation. But remember, when there's no unit involved, you should assume it's in radians. So tan of 3 is talking about 3 radians. Now, how can we even begin to think about 3 radians? Well, we should start with pi radians, because pi, if you recall, is approximately 3.14. And so 3 is almost 3.14, but not quite. So intuitively speaking, 3 radians should be almost pi radians, but not quite. So it should look something like this. And so tan of 3 would be the slope of that radius, which you can tell is going to be a negative number. So tan of 3 is negative. Another way to convince yourself that tan of 3 is negative is to think about sine over cosine. The sine or y-coordinate of that point is positive, and the cosine or x-coordinate of that point is negative, and a positive number over a negative number will equal a negative number. So it's another way of realizing why tan will be negative. All right, what about cosine of 1 degree plus cosine of 91 degrees? Well, if we're going to have any chance at all, we should start by thinking about where 1 degree is. And so 1 degree seems like it's probably very close to this 0 degree point. So maybe something like that. Maybe that's 1 degree. And so the cosine of 1 degree looks like it's probably almost close to 1, right? Like a large positive number close to 1. What about cosine of 91 degrees? Well, 91 degrees is just 1 degree past 90. So it's probably really close to this point over here. So this is a horrible radius, but something like that. And if that's 91 degrees, then the x-coordinate of that, or the cosine of that, is some very tiny negative number. So it's negative, but nowhere close to -1. So when you add something that's very close to 1 to something that's just barely negative, you're going to get a positive number. Next question. If you knew for a fact that 2 angles, θ1 and θ2, had the same sine, can you conclude that they have to be the same angle? Or in other words, if sine of theta 1 equals sine of theta 2, can you cancel out the signs, so to speak, and determine that theta 1 must be theta 2? Well, it might be helpful to think about a specific example, like sine of 30 degrees. Is there any angle out there that's not 30 degrees that has the same y-coordinate or sine as 30 degrees? Well, if you start at 30 degrees and make one full rotation, you end up at 390 degrees, which is technically a different angle, even though it's coterminal with 30 degrees. And since it's coterminal, it definitely has the same y-coordinate or sine, so sine of 30 degrees is the same as the sine of 390 degrees. So the answer to this question is no. You cannot conclude that theta 1 is theta 2. You might, in fact, have coterminal angles. But interestingly, there's also answers that are not coterminal with 30 degrees. Can you find an angle theta that has the same sine as 30 degrees but is not coterminal to it? Well, sine is the y-coordinate, and using the symmetry of the circle, there's definitely a point on the opposite side of the circle that has the same y-coordinate as 30 degrees, and that would be 30 degrees off of the negative x-axis, which would be 150 degrees. So the sine of 30 degrees is also the same as the sine of 150 degrees. Interesting. So those were a few fun problems. In the next video, we will tackle how to graph sine, cosine, and tangent.